Hi, this is Shoikat Mujumdar. Today we will discuss Introduction to Quantum Mechanics under the module Quantum Mechanics. The learning objective is to acquire working knowledge of the quantum mechanics postulates on the physical systems. Background. Classical theory of physics is based on some basic laws. Commonly, these are Newton's laws of motion, gravitational law of attraction between two bodies, Coulomb's law of attraction or repulsion between two electrically charged bodies, Lorentz force equation related to the force on a moving charged particle passing through a magnetic field. It has been observed that classical theory of physics can explain successfully the motion of the celestial bodies or other observable objects. There are few phenomena which the classical mechanics failed to explain. The phenomena are: number 1, stability of atom; number 2, spectral series of hydrogen atom; number 3, black body radiation. Max Planck in 1900 at a meeting of German Physical Society read his paper on the theory of the energy distribution law to the normal spectrum. This was the start of the revolution of physics, that is the start of quantum mechanics. Stability of atom. As per Rutherford's model, electrons revolve round the nucleus. This is the electron, it is revolving round the nucleus in a circular path, but particles that are in motion on a circular path would undergo acceleration. This particle will undergo acceleration, and acceleration causes radiation of energy by charged particles. So it will radiate energy. Eventually, electrons should lose energy and fall into the nucleus. As it is revolving round, one rotation after another rotation, it is losing its energy, should lose its energy, and as per Rutherford model, it should collapse onto the nucleus. But it contradicts the observed fact of the stability of atom. That means the electrons never collapse onto the nucleus. Atom is stable. Classical physics failed to explain the stability of the atom. Spectrum of the hydrogen atom. According to classical theory, an excited hydrogen atom radiates energy of all wavelengths continuously, but experimentally it has been observed that the excited atoms of hydrogen emits electromagnetic radiations of certain definite wavelengths due to transition of an electron from higher energy state to the lower energy state, corresponding to Lyman, where N1 is equal to 1, Balmer, where N1 is equal to 2, Paschen, where N1 is equal to 3, bracket N1 is equal to 4, and Hund series, where N1 is equal to 5. This discrete set of lines represented by the following formula: 1 by lambda, it is a wave number, or it may be represented as nu bar, is equal to RH. RH is the Rydberg constant. For hydrogen, its value is 1.09677576 10 to the power 7 meter inverse. Z square, RH into Z square, 1 by N1 square minus 1 by N2 square. If N1 is equal to 1, then N2 will start from 2, 3, 4. N1 is equal to 2, then N2 start from 3, 4, 5 and so on. RH is a Rydberg constant whose value is constant because of this value m e to the power 4 by 8 h cube c epsilon naught square. For heavy elements, R becomes 1.0973731 into 10 to the power 7 meter inverse. This value is slightly different from hydrogen atom. In a generalization of classical physics that includes classical laws at special cases, quantum physics extends that range to the region of a small dimension. Just as c, that is the velocity of light, signifies universal constant, Planck's constant characterizes quantum physics. H is equal to 6.65 10 to the power minus 27 arc second, or 6.65 10 to the power minus 34 joule second. Particle nature of radiation. Radiation of energy is usually characterized by its wave-like nature. But many experimental observations such as blackbody radiation, photoelectric effect, Compton effect, pair production, etc. cannot be explained properly only by considering the wave nature of radiation. But many experimental observations such as blackbody radiation, photoelectric effect, Compton effect, pair production, etc. cannot be explained properly only by considering the wave nature of radiation. This phenomena, along with any natural phenomena, can be properly explained on the basis of particle aspect of radiation. In that case, the wave of electromagnetic radiation behave like particles of definite momentum and energy. Let us see this animation. Electrons is emitting when light is falling on the metal surface. An electron is emitting from the metal surface when light of suitable wavelength is falling onto it. This is the photoelectric effect. Now come, let's start the photoelectric effect. The emission of electrons from a metal plate when illuminated by light or any other radiation of any wavelength or frequency must be suitable frequency, is called photoelectric effect. The emitted electrons are called photoelectrons. This is the metal plate where light of suitable wavelength is falling onto this one, and electrons are emitted, and these electrons are collected by the collected plate, and there is a current in the circuit and there is a deflection in the emitter. So the electrons that are emitting is known as photoelectron. The current that we are getting is known as the photoelectric current, and the effect as a whole is known as the photoelectric effect. Experimental findings of the photoelectric effect. Number 1, there is no time lag between the arrival of light at the metal surface and the emission of photoelectrons. Number 2, when the voltage is increased to a certain value, say V0, the photocurrent reduces to 0. Number 3, increase in intensity increases the number of photoelectrons, but the electron energy remains the same. Increase in intensity means increase in the number of photoelectrons. Number of photoelectrons. This is the increase of photoelectrons. That means we are getting the more photocurrent, but the electron energy remains the same. There is no change in the electron energy. Increase in frequency. This is the change in frequency. Increase in frequency of light increases the energy of the electrons. Increase the energy of the electrons at frequencies below a certain critical frequency. No electron is emitted. This particular frequency is known as the threshold frequency, below which there will be no emission of electron, above which electrons will be emitted. This frequency is known as the threshold frequency. Einstein's photoelectric effect explanation. The energy of an incident photon is utilized by two ways. Number one, a part of energy is used to free the electron from the atom, known as photoelectric work function. First one is photoelectric work function. Some amount of energy of the incident light, it will be absorbed by the metal surface, so that the electrons are just on the metal surface, just on the surface of the metal surface. No electron is liberating, they are just ready to liberate. Other part is providing the kinetic energy to the electron, that is half mv square. So this is the energy of the incident photon is equal to h nu. This part is photoelectric work function, that means electrons are just ready, then they are getting the kinetic energy. So h nu is equal to W naught plus half mv square. This is the Einstein's photoelectric equation. Now h nu is equal to W naught plus kinetic energy maximum. This is maximum kinetic energy through which the electrons are moving. So W is equal to, we can write h nu naught. This is the initial frequency, threshold frequency. So this is the energy W naught. This amount of energy is absorbed by this metal surface, so that the electrons are at the just on the metal surface. If nu less than nu naught, no photoelectric effect. That means if the frequency of the incident light is less than the threshold frequency, then there will be no liberation of photoelectrons. So we can write W naught is equal to h nu naught is equal to hc by lambda naught. Lambda naught is equal to hc by W naught. Put in the value of h and c, we can convert this one is as 12,400 by W naught, or W naught we have written in the form of electron volt angstrom. If V naught is the stopping potential, just come back to the previous slide. Here it is in reverse bias. That means electron, this negative potential is barring the electrons to come from the positive plate to the negative plate. So that means it is the potential that is applied so that no electron can liberate from the metal surface. This is the stopping potential. So come to the stopping potential. If V naught, suppose V naught be the potential that is applied in reverse bias so that no electrons is. If V naught is stopping potential, then kinetic energy maximum is equal to h nu minus nu naught. So this maximum kinetic energy, that is the V naught is the applied potential, multiply the electron charge, E V naught is equal to h nu minus h nu naught. Thus V naught is equal to h nu by E minus h nu naught by E. This is the form y is equal to mx plus c. The graph with V naught on y-axis and nu on x-axis will be a straight line with slope h by e. So knowing the values of different frequencies and applied voltages, we can find out the Planck's constant experimentally in our lab. So we have to do this experiment in our lab. Photons. Einstein postulated the existence of a particle called a photon. To explain detailed result of photoelectric experiment, energy of a photon is equal to h nu is equal to hc by lambda. Photon has zero rest mass. Always remember, zero rest mass. Travels at speed of light. It explains instantaneous emission of electrons in photoelectric effect, frequency dependence. Some important definitions. First, radiation. According to Maxwell, when a charge is accelerated, it creates some electric and magnetic fields which are correlated to each other. They can move in form a wave on space with finite velocity. These are known as electromagnetic radiation of the velocity of the radiation, and it is given by V is equal to 1 by root over mu epsilon. In free space, V is equal to velocity of light, c is equal to 1 by mu naught epsilon naught to the power half is equal to 3 into 10 to the power 8. Theoretically, the wavelength lambda of these radiations may have values from lambda tending to 0 to lambda tending to infinity. Some examples of EM waves are visible light in the range of 4000 angstrom to 7800 angstrom. X-rays, its wavelength range is 0.1 angstrom to 10 angstrom, etc. Reaction of matter on radiation. Let us see what happens when some radiation is incident on a surface. There are three possibilities. Some part of radiation may be reflected, some part of radiation may be transmitted, and some part of radiation may be absorbed. From conservation of energy, we can write Q is equal to, Q is the total energy of incident radiation is equal to energy absorbed plus energy reflected plus energy transmitted. So we can write 1 is equal to A plus R plus T. What is A? A is, if you divide this equation by Q, then this is 1 by QA by Q plus QR by Q plus QT by Q. So QA by Q is A, is known as absorptive power. R is QR by Q is known as reflective power or reflection power. T, transmittive power or transmission power. T is equal to QT by Q. Black body. What is black body? A black body which absorbs all the incident radiations. Clearly, for a black body, absorptive power is equal to 1 and reflective and transmittive power is equal to 0. The best black bodies in nature are lamp black, whose absorptive power is 0.96, and platinum black, its absorptive power is 0.98. But for experimental purposes, one can prepare a cavity having absorptive power almost equal to 1 with inner walls polished with platinum black. Radiations by hot bodies. When a hot body is heated up, or when a hot body is heated up, it changes its colors. This is because it emits radiations. At first, we see the color of a hot body is red. Then it becomes some orange, and at last, after reaching certain temperature, it becomes white. This all signifies that hot body emits radiation of high wavelength and low temperature. At high temperature, it also emits the radiation of lower wavelength. Black body radiation. When a black body is heated up and kept at a fixed temperature, then electromagnetic radiations are emitted from inner walls of the cavity. This is black body. This radiation is partially reflected and absorbed by the inner walls of the black body itself. After some time, the cavity is filled up by electromagnetic radiation. The temperature of the black body is kept fixed. This implies that the radiation is in thermal equilibrium. This means that electromagnetic radiation emitted per second by the walls of the cavity is the same as absorbed. In thermal equilibrium, the energy density of the electromagnetic radiation remains constant. As we have a hole in the cavity, the radiation comes out from this hole, which is a part of inside radiation. Now, energy density. What is the energy density? At a particular temperature T, energy in the cavity per unit volume is called energy density. That means energy per unit volume. It is denoted by U. Spectral energy density. These are certain definitions. It will be required later on. At a certain temperature, the average energy density between the wavelength range lambda and lambda plus d lambda. D lambda is very small. Lambda and lambda plus d lambda is given by U suffix lambda d lambda. That means U is dependent upon lambda. Where U, lambda is called spectral energy density. The relation between U and U lambda is capital U is equal to integration 0 to infinity U lambda, here U is a small d lambda. One can use the frequency spread. Then instead of U lambda, we will use U nu. U suffix nu. This is defined frequency range nu and nu plus d nu. Emissive power. Total radiation energy emitted by unit surface area of the black body at a certain temperature is called emissive power of the black body. It is denoted by E. It will be used frequently for different derivation purpose. Here we will discuss later on. Spectral emissive power. The total radiated energy between lambda and lambda plus d lambda range. That means the spectral range, wavelength range is lambda and lambda plus d lambda. This is small, d lambda is small. Emitted by unit surface area of the black body. Always remember unit surface area of the black body at certain temperature is given by E lambda d lambda. That means the emissive energy density within the wavelength range is lambda and lambda plus d lambda. Or in other way, energy radiated between lambda and lambda plus d lambda by unit surface area of the black body. So E lambda is called spectral emissive power of the black body. It is clear from the definition that the energy E or emissive power is equal to integration 0 to infinity E lambda d lambda. If we know E lambda at a certain temperature, we can find U lambda by the following relation. U is equal to 4 by C E lambda, where C is the speed of light. Already we have discussed U is equal to integration 0 to infinity U lambda d lambda, where this U is the spectral energy density. Spectral energy density. So again, coming back to this slide, there is a relation of spectral energy density with U lambda, and this U, its relation with the spectral emissive power is 4 by C E lambda, where C is the speed of light. So we have to remember this E lambda and this relation U is equal to 4 by C E lambda.